Hi, we're going to look at 2.2a, continuous functions. You've seen continuous functions before. Basically, they're functions that if we were to draw them, we never lift our pencil up to go back down. We can just continue in any direction. So that's continuous. A parabola is continuous when it's going towards a asymptote but never gets there. That's still continuous as well. Okay, let's look at some examples that are not continuous. Okay, let's say we have a line, but then at this point it does not exist. Okay, even to draw it, I had to lift up my pen. So this is not continuous. Okay, let's draw another one. This one's going to be a little bit more obvious. Here we have a point here, and then there's an open space, and then it carries on. Okay, this is also not continuous because I picked up my pencil to go and do the rest. All right, now what's cool about continuous functions is the limit will always exist at continuous functions. Now let's see why that is. Let's just put a point right here, okay? I'm going to call this point A. Coming from the right where x is getting smaller and smaller towards A, we can see that we're going here and then here and then here, and we're going up to this point. So that's the limit. And going from the left, here we have points going towards A, and we get to that same point. So any continuous function, the limit exists. Now here the limit does exist, but it's not continuous. What we're trying to say is any continuous function, the limit does exist. So let's go ahead and write that down in a more formal definition. Okay, for continuous functions. For continuous functions, okay? I'm going to go ahead and draw a little tiny graph here as an example. Same thing as before. I'm going to call this point A. I'm going to draw a line here. Okay. So for continuous functions, the limit of f of x as x approaches A is f of A. Okay. For continuous functions, the limit of f of x as x approaches A is f of A. For example, this is A. This right here is f of A. Okay, if we approach A from the right, this graph comes to this point. If we approach A from the left, this graph goes to that point. So there the limit exists, and it happens to be f of A. Okay? All right, and if you think about it, we can just say f of A equals L, where L is the limit. Let's do some examples. Let's look at the limit of 3x plus 5. The limit of 3x plus 5 as x approaches 2. All right. Well, is 3x plus 5 a line? Well, of course it is. Y equals mx plus b. This is a line. A line is continuous, so we can evaluate and put the 2 straight in there. So we have 3, 2 plus 5, which is 11. So that would be our limit. Okay, let's look at another example. The limit of x squared as x approaches 7. Here we have a parabola. A parabola is continuous, so we can evaluate and go ahead and put it right in, and it's 49. Okay, let's look at one more. The limit of log of x as x approaches infinity. Oh, not infinity. I meant to say 100. Okay, the limit of log of x as x approaches 100. Let's look at the log function. Okay, we know log of 10 equals 1. Okay, log of 100 equals 2. And this is pretty much the graph. All right, so we have log of 1 equals 0 because 10 to the 0 equals 1. So this is log of 0. Log of 10 is 1, and log of 100 is 2. If you can imagine drawing something like this. There's 1, there's 2. Okay? So we have continuous function. This is log. It says the limit of log of x, where we already know this is the graph of log of x, which is continuous. Therefore, we can evaluate. We can put log of 100 in there, which we know is 2, because 10 to the 2 equals 100. All right, very good.